My name is Greenwood.
I'm AlShareef.
I'm Mohammed, Basyouni. Okay, so my name is Mohammed Basyouni. After graduating from Northeastern University, I'll be working with Yanbu National Petrochemical Company in Saudi Arabia, the Royal Commission of Yanbu Industrial City.
So my name is Marshall Greenwood. I'm graduating in chemical engineering. I plan on studying energy in the future and looking into jobs in like the nuclear energy center.
I'm AlShareef, and after graduating, I'll be working in Sabic Technology Center in Jubail, Saudi Arabia. Our group mentor is Mrs. Gretchen Govoni. She is a chemical engineer with more than 10 years of experience working for multiple companies. Now she is a corporate sustainability director at Sabic, focusing on corporate sustainability strategies by building sustainability programs and processes, and by products, synergy, and cross-integration between plants. Project insight and design objectives. The idea of our project came after the Saudi Basic Industries Corporation (SABIC) joined a joint venture with the Saudi Acrylic Acid Company to build the world's largest acrylic acid plant. The design capacity of this plant is 330,000 metric tons per year of high-purity acrylic acid, and the plant is located in Jubail Industrial City in Saudi Arabia. We found this as a great opportunity for us to gain a valuable experience and knowledge about acrylic acid production and about the petrochemical industry in general. Now let's have a brief background about the product. Acrylic acid is an organic compound with the chemical formula CH2 double bond CHCO2H. It is called also propenoic acid. It's the simplest unsaturated carboxylic acid, and it is widely used in the manufacture of various products such as paints, plastics, coatings, and many others. The market analysis for acrylic acid shows that the global demand is estimated at 5,750 kilotons in 2014, valued at $15.5 billion, and it is expected to witness a growth of roughly 6% from 2015 to 2022, driven by the increase in demand for superpolymer absorbents, especially in developing countries. Acrylic acid is expected to generate revenue of $22.5 billion by 2020, growing at a compound annual growth rate of 6.5 between 2015 and 2020. The Asia-Pacific region is the world's largest market for acrylic acid and its derivatives, with China being accounted for more than 25% of the global demand. The current acrylic acid price is valued at $2.5 per kilogram. Various methods have been developed to produce acrylic acid in an industrial scale. The first one is via the catalytic partial oxidation of propylene, and this method has two different paths. The first path is via the two-step vapor oxidation of propylene to acrylone and then to acrylic acid, requiring two reactors in series and utilizing two separate catalysts. This method provides 94% conversion of propylene to acrylic acid, which makes it the most commonly used in the industry. The second path is via the one-step vapor oxidation of propylene to acrylic acid in one reactor and utilizing one catalyst. Typically, this provides 65 to 73% conversion of propylene to acrylic acid. Some of the other methods developed include acetylene-based routes, hydrolysis of acrylonitrile, and ketene processes. However, these methods are not used due to environmental and economical considerations. For the catalyst choice, two catalysts have shown to have a reasonable conversion of acrylic acid and selectivity. The first one is vanadium pyrophosphate. It has a product conversion of 65%. And the second is the mixed metal oxide systems, which provide a product conversion of 73%. The main objective of this project is to design a process to produce acrylic acid, focusing on efficiency using least amount of inventory and work in progress to achieve the minimum possible yield. The proposed design specifies a one-reactor system to convert propylene to acrylic acid in one-step reaction. And it implements two patents. The first is for the selective oxidation of propylene to acrylic acid, and the second is for the addition of a recycled stream to the process. Combined, a conversion of 88% of propylene to acrylic acid is promised, as the patent states. The main goal of this project is to produce 60,000 metric tons per year of 99.9 mole% purity of acrylic acid product, while improving the product yield and minimizing byproducts. Now let's move to an overview of our process. Our process design consists mainly of two parts. The first is the selective oxidation of propylene to acrylic acid in a fixed bed reactor packed with our selected catalyst. The catalyst will be reloaded every 6 months. The second step is a series of separations that involves one flash drum and 4 separation towers. So at the beginning of the process, air, steam, and propylene are fed to the reactor, and after the course of the reaction, the effluent stream leaving the reactor contains acrylic acid, acetic acid, carbon dioxide, nitrogen, and water, and it has to be cooled down as quick as possible to prevent products from further oxidation and dimerization. After it's been cooled, then it's fed to a flash drum in which the gaseous materials are separated from liquid materials. Gases will escape the drum from the top. The gaseous stream contains acrylic acid, water, carbon dioxide, nitrogen, and oxygen, and this stream will be partially recycled back to the reactor, as in the second patent we're implementing in the design, and the rest of the stream will be pumped to an absorption tower, in which the ionized water is used to absorb acids while letting the other gases to escape and to be purged. And after that, the bottom liquid stream of the absorber is mixed with the bottom liquid stream of the flash drum, and both are introduced to a liquid-liquid extraction column in which an organic compound, diisopropyl ether, is used to extract acids from water. Water will leave the column from the bottom, while acids and the solvent will leave from the top, and then they are fed to a solvent recovery tower, in which acids are separated from the solvent. The final stage of separation is the separation of acrylic acid from acetic acid in a distillation column. Acrylic acid is collected at the bottom of the column, and acetic acid is collected at the top of the column. Some of the challenges we had to consider in this design: the first one is to meet the Kingdom's and SABIC's emissions regulations by meeting sustainability measurements, to reduce greenhouse gases emissions and energy intensity, also to further improve final product yields and conversion, and to maintain a thermal stability of reactants and products. Now let's move to mass and energy balance calculations. First, we have the mass balance around the reactor. On the right side of the screen, the stoichiometry of the reaction is shown. Reaction 1 is the reaction of the oxidation of propylene to acrylic acid, and this reaction is accompanied by two-side reactions which generate acetic acid and carbon dioxide as byproducts. The molar flow rate of acrylic acid was determined based on our annual production, and using this information along with conversion and selectivity values specified by the catalyst, we are able to perform a mass balance around the reactor, and results are presented in this table. We see that the composition of propylene in the feed stream is 5.6 mole%, which is within the lower and upper explosive limits for a packed bed reactor operating at the typical temperature for this reaction, which are between 2.4 to 11%. Secondly, we have the mass balance around the flash drum. We're assuming that there is no flow of oxygen, nitrogen, carbon dioxide, propylene in the liquid flash stream. We're also assuming that there is no acetic acid flow in the vapor flash stream, and liquids and vapors in the flash drum exist in equilibrium and following the vapor-liquid equilibrium model. So to solve the general mass balance equation for the flash drum, we have constructed a system of 6 equations with 6 unknowns. Solving this system concludes our calculations for the mass balance, which are shown in this table. Now, let's move to the mass balance around the absorber. We're assuming that full absorption of acids is achieved. Therefore, off gases stream does not contain water, acetic acid, or acrylic acid. In order to solve the general mass balance equation, we performed components mass balance around the absorber, and after putting all knowns together, the general mass balance, that brings the general mass balance equation to this form. Another assumption we made based on analogous process, the amount of deionized water entering the column is taken as 4/3 the amount of liquid stream leaving the column. And that concludes the mass balance calculations for the absorber. We calculated the carbon dioxide annual emissions, and we found it to be equal to 14.2 tons per year, which is classified by the US EPA as moderate emitter. The mass balance around the mixing point is basically adding the liquid flow stream coming from the absorber and the liquid flash drum coming from the flash drum, and results are shown in this table. For the mass balance around the liquid-liquid extraction column, we assume that the ratio of solvent added relative to the amount of water removed is 1.1 based on a similar process, and that concludes the mass balance calculations for this part. For the mass balance around the solvent recovery column, we're assuming that complete recovery of solvent is accomplished, and the bottom's product contains only acrylic acid and acetic acid. And 7, for the mass balance around the acrylic acid recovery column, we're assuming that 99.9 recovery of acrylic acid is accomplished at the bottom. And after we performed components mass balance, we had a system of 2 equations and 2 unknowns. Solving this system gives the bottom's flow rate and the distilled flow rates and concludes the calculations for this part. Now for the reactor energy balance, according to the kinetics of the reaction and the specifications of the catalyst, the reaction temperature needs to be maintained within 190 to 330 degrees Celsius in order to avoid cork formation and further oxidation bubbling. And since the reaction is highly exothermic, temperature of 191 degrees Celsius is assumed to be enough to be fed to the reactor, since there is enough heat at the inlet of the reactor to heat the feed to a temperature adequate to initiate the reaction. The temperature of the reactor in this design is maintained within 250 to 310 range to give highest conversion. Therefore, the energy balance can be determined to find the heat must be removed in order to get an outlet temperature of 310 degrees Celsius. Using the following expression to find the change in enthalpy in reactive processes, assuming the pressure effect is negligible, and from the energy balance, which shows that the heat flow equals the change in enthalpy, we obtain the necessary data to do the calculations from literature, and we successfully performed an energy balance over the reactor, and we found that the heat needed to be removed from the reactor to maintain a temperature of 310 degrees Celsius, and the output of the reactor is equal to 89.6 million kilojoules per hour.
Okay, just a quick overview about our reactor design and process design. As mentioned before, acrylic acid is produced via catalytic partial oxidation of propylene in a packed bed reactor in one step. The reaction is a heterogeneous catalytic process with multiple phases, the catalyst being in solid phase and the reactants and products are in gaseous phase, and the actual reaction occurs on the surface of the catalyst inside our packed bed reactor. So according to our kinetics, the reaction rate would decrease rapidly when operating at temperatures lower than 250 Celsius degrees, and temperatures higher than 330 Celsius degrees will alter the composition of our catalyst, causing some of the substances inside the catalyst to evaporate. Therefore, the temperature must be maintained between 250 and 330 Celsius degrees. That's why we integrated a heat exchanging system inside our reactor, which which is a shell and tube heat exchanger with a counter current flow. So to mathematically size our heat exchanger, we used the basic heat equation. We calculated the difference in temperature, the logarithmic mean of the difference in temperature. And from the energy balance I mentioned before, we were able to obtain the heat that needs to be removed from our reactor, and the overall heat transfer coefficient for tubular heat exchanger was found from literature, and it's equal to 150. And we were finally able to solve for the surface area of our heat exchanger. After that, we calculated the length of the tube using the stated equation. The weight of the catalyst was determined previously. It will be supplied in 2 loads to our reactor manually, once every 6 months, so twice a year. The void fraction was found from literature, and plugging back all of the parameters, we were able to find the length of each tube inside the heat exchanger. After that, we solved for the number of tubes inside our heat exchanger using Ergen's equation for packed columns. After solving for the superficial velocity and rearranging, we were able to find the number of tubes, which is 613 tubes inside the heat exchanger. So the last parameters we had to calculate to size our reactor were, for one, the cross-sectional area of the bundle of the tubes, and from that we were able to estimate the the surface area of our reactor, and from the surface area of the reactor we found the diameter of the reactor, and we were able to estimate the length of the reactor using that expression, and finally we were able to obtain the volume of our reactor, and it's equal to 27.1 cubic meter. Here's just a quick summary of what I just mentioned. For the material of construction of our reactor, we are using carbon steel, as it's the most commonly used material for this process. And there's our reactor. It will be held vertically with an integrated heat exchanger in the center, with an opening to the top and the bottom to let our cooling reagent to enter and leave whenever it's needed, utilizing gate valves and automatic valves to maintain it within the required temperature. So after sizing our reactor and finding the dimension of the heat exchanger, we had to make sure that to account for the cooling process and make sure it is within the desired limits. So we decided to use high-tech molten salt as a cooling reagent, because it has low melting point, thermal stability, and low cost. And using that expression, we were able to find the amount of molten salt supplied to our heat exchanger. So after cooling our reactor, we had to account also for cooling the effluent or the products coming out of our reactor. As temperatures higher than 90 Celsius degrees would cause dimerization and polymerization of our reactants. So we used we integrated the refrigeration system to maintain it within the limits at temperature of 50 Celsius degrees, and we solved the 2 expressions simultaneously to finally obtain the amount of heat that needs to be removed from our effluent. After that, we come to the economical calculations. We start off with estimating our raw materials and utility consumption. The raw materials includes two main components: the feedstock, including water and propylene, and catalyst loads. As I mentioned before, we are loading our catalyst twice a year manually for economical purposes. And here we have the profits we are making, and to maximize our profit, we decided to sell our byproduct, one of the most essential byproducts, which is acetic acid. One thing to mention is that the water cost was included in the utility cost, as water is going to be fed in a process stream, and all of the utility costs are based on Saudi Arabia's rates of energies for industrial facilities. So after that, we estimated the manpower requirements for our plant. We started with calculating the number of operators per shift using the stated equation, and for that we had to calculate first the number of main equipment we have, which I will illustrate later on in the presentation. So we came up with the number of the operators per shift, and from literature we found that for continuous processes we need four 4.8, on average we need 4.8 shifts, so multiplying that with our operators per shift, we found that we need 15 operators in our plant. And the average salaries and supervision and direct overhead are based on Saudi Arabia's salary rates. So after that, we estimated the cost of production of our plant. So to do so, we first started with the inside battery limit of our plant using a Lang factor of 4.74, which was found in literature, and using an estimate that the outside battery limit is 40% of the inside battery limit, we were able to find the cost of the ISPL plus the OSPL, which by finding it, we will be able to calculate the variable and fixed components, and they are all mentioned here in the tables. So finally, we estimated the equipment cost to build construct our facility. So in the table, we see all of the equipment we are using to construct the plant. Just one thing to mention is that some of the prices required further knowledge about the duties and functionality of each unit. So we had to contact our suppliers directly to get specific quotes about the prices. So some of the prices that we weren't able to obtain, we just estimated an average based on the process.
So part of our economic analysis was deciding where we're going to actually have the plant. We decided to locate in Saudi Arabia, in Jubal Industrial City. So the position allows for easy exportation and access to like the foreign markets. It's one of the largest industrial complexes in the world and has an oil refinery, industrial seaports, chemical suppliers, all within like the same area. It also allows access to low feedstock as well as low energy rates, subsidized by the government. We looked at a discounted cash flow analysis to find the net present value over 10 years, and we estimate a 15% discount factor to assume for a moderate, like conservative risk while we're doing our project. And we calculate the net present value over 10 years to be $164 million over that assumed period of the life of the plant. So we have over here just a viewpoint of each net present value per project year, starting out low, but paybacks by the third year. And as we see, 164 before. Next slide. So this is just a summary of what we're expecting to get a revenue. It's $152 million based on the output of acrylic acid and the market demand. And after the tax and depreciation, we're looking at a net income of $78 million per year, hopefully. So next thing is safety and process control. So the first one for the reactor would be a control system. We're looking at a feedback and feed-forward control system. We want to have the temperature set between 250 and 330 degrees Celsius. And the temperature product is always maintained below 310 degrees to prevent polymerization. Two temperature controllers, as we can see over here and over here, are used to maintain the rate of steam from the feed control. For the heat exchanger that's cooling the reactor, the pressure control connected to the pressure valve. In the case of a pressure valve, in the case of the pressure being too high, it will release the valve and decrease the pressure. So the next control system we have is for the flash control. It's conventional feedback control. Ensures that the mass balance does in fact balance and the separation of the liquid and gases. We're looking at a system that regulates the pressure of the liquid flow rate, and if the flow of the vapor is increased, then the pressure will decrease significantly and the feed rate will have to increase. We also have an absorber control system. The feedback system is to ensure sufficient separation for the carbon dioxide, and we're also looking at the gases leaving the liquid stream of the absorption tower. The rate of absorption is maintained by controlling the composition of the gases that are being purged, and we're assuming that the tower operates at steady state conditions, and there are negligible heat effects in the column. The last control system we have is for the distillation and extraction towers. It's a simplified arrangement, and it suggests the control of the extraction column, the recovery column, and the acid recovery column as well. So the product composition is controlled by fixing the column temperature and by letting the temperature control manipulate the distillate flow. The pressure controller manipulates the bottom flow in order to avoid pressure buildup. And you can see right here, there's the pressure sensor connected to the buildup. So some health hazards and concerns that we're looking at, there have been National Institute of Health and Safety has established like a recommended exposure limit, as well as the recommended limit for occupational exposures. Furthermore, we're looking at ASGAHI, which has assigned like threshold limit values, and it's the level which is believed that a worker can be exposed day to day. And we have these values for the products that we have summarized in the next table. So here we have carcinogen, the symptoms of health effects, and also those values, the limits of exposure for acrylic acid, acetic acid, propylene, and carbon dioxide. And also here is the physical properties of those same components, and as well as their reactivities. We don't want to mix anything, with an oxidizer, and that would be bad. So the last one, go back actually. So for storage and handling, we need to add inhibitors to the acrylic acid. Otherwise, it will start to form polymers in case of exposure to heat or light. So the acrylic acid has to be stored in natural air rather than like inert gas, because that could cause that could affect the inhibitor that's being added to it to prevent the polymerization. So one commonly used inhibitor is monomethyl ether of hydroquinone. And additionally, to make sure that the inhibitor is equally distributed during storage, we're going to recommend like well mixing of the tanks, flipping them every so often as well in the storage facility. For bulk storage, the recommended temperature is like room temperature, 15 to 25 degrees C. There should be no steam used to heat or thaw acrylic acid because it could react with the water. All the acrylic acid vessels, including the charge and the weight tanks, should have a high temperature alarm, because in case of the higher temperature, it could quickly initiate polymerization. Also, we want to avoid freezing when possible, because when the product is frozen, all the impurities tend to concentrate on one side of the product, and we don't want that high level of concentrated impurity. Another thing that we looked at was trying to model our whole process through Aspen. This is basically like a flow diagram that we use, and we're trying to look at bringing back in the recycle stream. The good thing for Aspen is it allows you that after you specify your whole process, you can make like tweaks within it and get real-time calculations back, and we're looking further into investigating that. Any questions or comments? All right, well, thank you very much.
Thank you.